Section 9.1 is systems of equations. I'm going to show you both methods or two methods how to solve systems of equations. So in example 1, we've already got a system written. We've got x plus 2y equals 0, 3x plus 7y equals 1, and we want to solve for x and y. I'm going to use substitution in this example. You could use both methods in any of the examples I show. I just want to be able to show you both methods. So in substitution, you want to get one of the variables by itself first. It doesn't matter which variable you pick in which equation. I'm going to pick the first equation and the variable x because I see that it's going to be the easiest to get by itself. Okay, so what you'll do is get x by itself, so I need to subtract the 2y. And I've got one of the variables by itself now, so then the next step, you take what you got and you plug it into the other equation for the variable that you got by itself. So I've got 3 times negative 2y plus 7y equals 1. And now we can solve for y. So I've got negative 6y plus 7y equals 1. Negative 6y plus 7y is just y. So we found our y. And then to solve for x, we just plug this back into one of the original equations. It doesn't matter which one you use. I'm going to use the top one because it looks simpler. So I've got x plus 2 times 1 equals 0. And then solve for x. So we've got x plus 2 equals 0 and subtract 2. You can leave your answer like this, or you can write it as an ordered pair. Remember, x comes first when you're writing an ordered pair. Okay, so negative 2, 1 is my answer. What you're doing here when you're solving a system of equations like this, remember these two equations are linear equations, so they're two lines. This answer is where they intersect. Okay, so these lines just intersect at one point, negative 2, 1. I'll show you a few more examples where you can see some different types of answers that you might get. Okay, so in the rest of the examples, I'm going to use elimination because I think a lot of people really like elimination the best. Some problems lend themselves to substitution, so it's good to know how to do substitution, but a lot of them, elimination just goes faster, so it's just a preference. Okay, so part B, I've got x plus y equals 20 and x minus y equals 8. And what you want to do in elimination is you want to get one of your variables to have the same coefficient and opposite signs. And this one already has that, so I don't need to do that step. They both have a 1 in front and they're opposite signs. So the next step is just to add the two equations together. So we've got 2x, the y's cancel, equals 28. And then we can solve for x. So we'll divide by 2. And we've got our x. And then the last step is just like the example that we did over here. You're going to plug this back into one of the two equations to get your other variable. I'll go ahead and plug it into the top equation again. So I've got 14 plus y equals 20. Subtract the 14, y equals 6. Okay, so again, these two lines intersect at just one point, 14, 6. Okay, well, sometimes you're not so lucky. You need to do something to at least one of the equations before you can get them to have the same coefficient, opposite signs. So let's look at a couple more examples. Part C, I've got 7x minus 3y equals negative 17, and negative 21x plus 9y equals 51. Okay, well, none of them have the same coefficient, opposite signs, but you are allowed to multiply any number you want as long as you multiply the whole equation by that number. It doesn't change your answer. Okay, so I'm going to look at the x's here, and I see that 7 times 3 gets me 21. So if I multiply this top equation by 3, I'm going to have a positive 21 here and a negative 21 here. That's what I want. So let's go ahead and multiply through by 3. So we get 21x minus 9y equals negative 51. Wow, and everything actually ended up canceling out. What that means is both of these equations were actually the same line. If you get 0 equals 0, or if you get the same number on both sides, what that means is you've got infinitely many solutions. They were the same line. If you graphed them, they'd be one line on top of the other. Okay, and then finally part D. I've got 2/3 x plus 4/3 y equals 1/3, and negative 2x minus 4y equals 5. Okay, again, there's not the same coefficient, opposite signs in front of one of the variables. Doesn't matter which one you work with, so let's just look at the y's this time. I noticed that if I multiply this one by 3, the 3's will cancel out and I'll have a 4y, and this one's a negative 4y. So I'm going to multiply the top equation by 3, and we get 2x plus 4y equals 1. Almost like the last problem, the x's and the y's cancel, so this side's 0, but 5 plus 1 is 6. So we just get something that's untrue. That's an untrue statement. Well, that just means the answer is no solution. And if you were to graph those two lines that you started with, you'd see that they were perpendicular to each other. Not perpendicular, I'm sorry, parallel. They never cross. Okay, so the two lines will never cross. That's where we have no solution. These were two parallel lines. If you have one where you get the same number on both sides, infinitely many solutions, it just meant that the two lines were the same. And then you can also get an answer where they just cross at one point. Okay. One other thing I want to add is you might have to multiply one equation by one number and the other equation by another number in order to get them to have the same coefficient, opposite signs. So don't be afraid to do what you need to do to get the same number, opposite signs in front of one of the variables. Okay, so let me know if you have any questions.